Assalamualaikum warahmatullahi wabarakatuh. Hello guys, my name is Yoris Suganda from Technique Engineering. This is a assignment one from Kimia Bahan. I will to tell you about development and application of aluminum alloys for aerospace industries. This is we have 5 topics. Firstly, abstract. 2, introduction. 3, specification and application of common alloys for aerospace. 4, characteristic of advanced alloy forming and processing methods and possibilities for aerospace application. And last, future of aerospace alloys requirement. Okay, first, abstract. Aluminum alloys have been the preferred choice the aircraft structural parts since the 1920s. Due to their lower density, improved fuel efficiency, and enhanced strength and hardness, all alloys can withstand high loads and vibration environments, ensuring long-term service life. They also have good corrosion and fatigue resistance, making them suitable for harsh aerospace environments. All alloys are also recyclable, reducing resource consumption and environmental load. Although composites have become more common in aerospace, high-strength all-alloys remain indispensable. This article reviews the progress and application of all alloys in aerospace, discussing common strengthening methods and advanced manufacturing and processing technologies. Okay, we go to second topic. The aerospace manufacturing industry reflects a country's industrial capabilities and primarily utilize materials such as aluminum alloys, steel, titanium alloys, and composites. While Ti alloys are valued for their high temperature performance and strength, all alloys are more widely applied due to their lower manufacturing costs and favorable properties, including high specific strength, low density, and good machinability. All alloys are extensively used in spacecraft structures and can reduce weight by 25% to 40% compared to steel. They constitute 60% to 80% of the weight in typical commercial aircraft, although composites are increasingly used in wide-body aircraft like the Boeing 787 and A350. The most common all alloys in aviation include the 2XXX, 7XXX, and all series. This is a application ratio of several structural materials in large commercial aircraft. Research and development of higher quality aluminum alloys have historically been driven by advancement in aerospace and military sectors. During the early aerospace industries, the focus was on reducing density while enhancing specific strength and stiffness, leading to the development of alloys like 2040, T60, and 7075. The demand for all alloys peaked during World War II, with the introduction of the 7075 alloy in the BE-29 bomber, marking the first successful application of a 7XXX series alloy in aircraft. Additionally, the first artificial satellite, the Soviet Sputnik, launched in 1957, was entirely constructed from all alloys, weighing 83.6 kg. In 1954, 3 Comet jets made from 7075 aluminum alloy crashed due to premature fuselage fatigue, highlighting the importance of damage tolerance. As aircraft designs evolved to include larger and thicker structures, stress corrosion cracking, or SCC, became a significant issue. Consequently, during the 1960s and 1970s, the focus shifted to enhancing damage tolerance durability and corrosion resistance in aerospace aluminum alloys. Advances in heat treatment such as the T73 and T76 process improve the microstructure and address SGC in the 7075 T6 alloy, albeit with a slight reduction in strength. New alloys and treatment developed during this period include 7475 T76, 7075 T74, and 2214 and T3. In 1969, Airbus adopted aluminum alloys as primary structural materials, coinciding with the first flight of the Boeing 747, which utilized high-strength aluminum as its main structural component. In the 1980s, rising fuel prices necessitated reduction in aircraft structure weight, while increased operational speeds required aluminum alloys to withstand higher temperatures. Aluminum, lithium, or Li alloys gain attention for their advantageous properties, including low density, high Young's modulus, high specific strength, and excellent fatigue and corrosion resistance. Substituting traditional alloys with Li alloys can reduce structural weight by 10% to 20% and enhance stiffness by 15% to 20%, contributing to improved aerospace equipment for performance and lower fuel consumption. Li alloy development has progressed through 3 generations, with the 3rd generation now widely utilized. Typical grades include 2795, 2796, and 2098, among others. Currently, all Li alloys are extensively used in advanced aircraft such as the Airbus A330, 340, 350, or 380, Boeing 747 or 777 or 787, and COMAC C919. Go to second topic, classification and application of common alloys for aerospace. First, cast alloys. Cast aluminum alloys are produced by cooling molten aluminum without additional processing, allowing for various shapes through different molds. Modern aircraft manufacturing utilize around 20 alloy parts, with application including components such as forward access door of the Boeing 737 and precision castings for baggage compartment doors and flap tracks. Commonly used cast alloys in aerospace include all silicon, all copper, all magnesium alloys, with all steel alloys being the most prevalent due to superior wear resistance, low thermal expansion, and excellent casting properties. All steel alloys account for 85 until 90% of aluminum casting and are commonly used in electronic packaging and engine parts and non-structural components. A representative grade A357 is used in the body and fuel tank and of the Alcoa AGME 86B cruise missile, comprising 80% of the projectile body and featuring large, high-precision complex casting. This is all alloys casting for aerospace application. All silicon binary alloys are aluminum alloys that can be strengthened through heat treatment to enhance their overall properties, allowing elements such as magnesium, manganese, and copper are added. Copper improves heat resistance and tensile strength but reduces casting properties and corrosion resistance. Magnesium enhances mechanical strength and corrosion resistance but can negatively affect casting performance. Manganese helps mitigate the adverse effect of iron on the alloy and improve heat resistance. Conventional cast alloys typically have needle-like eutectic silicon and coarse primarily silicon in their microstructure, which can lower strength and plasticity. to refine the microstructures and improve properties. Inoculants like niobium, boron, sodium, strontium, and antimony are often added. For instance, adding NBB inoculants can significantly refine the microstructures and enhance the mechanical properties of alloy alloys. The yield strengths or ES of these alloys generally range from 150 to 350 MPa. Compared to all silicons alloy alloys, all copper class alloys offer superior mechanical properties, cutting performance, high temperature of performance, and edge hardening capabilities due to the presence of the also Cu reinforced base. These alloys are primarily used for structural components that operate at elevated temperatures or bear significantly loads at room temperature. Among all Cu alloys, the all Cu5M and CDV alloy stands out for its high strength and precision, being alloy mainly with copper, manganese, titanium, and trace amount of zirconium, cadmium, vanadium, and boron. This alloy is particularly suitable for aerospace application due to its excellent mechanical performance at both high and room temperatures. Research by M. et al. On N2 TiB2 TiC particularly reinforced all Cu alloy demonstrates impressive mechanical properties with yield strength and ultimate strength values at various temperatures. So, deformed all alloys. Deformed aluminum alloys are produced by first casting molten aluminum into ingots, which are then processed through methods like stamping, bending, rolling, and extrusion to alter the microstructures and shape. Compared to cast all alloys, deformed all alloys have lower alloying element content, higher density, and a more uniform microstructures and superior mechanical properties, although they are generally more expensive. These alloys are classified into heat-treatable and not heat-treatable categories, with the boundary defined by the solubility limit of a saturated solid solution at room temperature. NHTL alloys, such as the All-Mn or 3XXX series and All-Mg 5XXX series alloys, are primarily through strain and solution strengthening. They are known for their excellent corrosion resistance, good plasticity, and weldability, but they have lower strength. All Mg alloys typically exhibit higher strength than all Mn alloys. Through their application in aircraft or limits, primarily being used in fuel tanks and oil pipes. In contrast, heat-treatable alloys offer higher strength but lower plasticity and corrosion resistance. The most commonly used heat-treatable alloys in aviation are quaternary and quaternary alloys with more complex compositions rather than simpler binary alloys. In the aerospace industry, deformed aluminum alloys are preferred over cast alloys due to their critical structural roles. Common heat treatment scheduled for 3XXX series alloys include 3 351, 339, 3H51, and 3H511, while the 7XXX series typically undergo treatment like T6, T65-1, and T775-11. All lithium or alloy alloys are treated with schedules such as 335 T3511 and T8511. And this is a comparison of tensile properties of three kinds of gas alloys. The most widely used deformed alloys in civil aircraft include the 7XXX series, 7 triple X series and alloy alloys, mainly 8 triple X series and some 2 triple X series. These alloys are utilized in various aircraft components, such as the skin, wings, and frames of large aircraft like Chinese C919, Boeing B777, and Airbus A318. For example, the lower wing and body skin, which experience tension, primarily use 2 triple X series alloys, such as 23, 24, 339 and 25, 24, 33, known for their high strength and fatigue resistance. The upper wings and floors, which endure compression, typically utilize 7 triple X series alloys like 7055, T7751, 51, which offers superior strength and corrosion resistance. Additionally, newer alloy alloys such as 2196 and 2099 are also being incorporated into the modern aircraft like the C919. The use of 2 triple X and 7 triple X series alloys is also prominent in the Japanese H-1 rocket, highlighting their versatility and importance in aerospace application. The 2 triple X series aluminum alloys are heat-treatable alloys, with copper as the primary alloying element, typically containing 3 until 7% Cu at 548 degrees Celsius. Cu has a maximum solubility in aluminum, which decreased to 0.55% at 302 degrees Celsius. The primary strengthening mechanism is precipitation strengthening with the formation of the alto Cu base. While increasing Cu enhances strength, heat resistance, and fluidity, it also reduces corrosion resistance and plasticity, and increases hot cracking tendencies. Magnesium is often added to improve strength and corrosion resistance through the formation of alto CuMg precipitates. Manganese can also be included to enhance corrosion resistance and strength while refining grain size. Common grades of 2 triple X alloys include 2017, 2024, and 2219. The 2024 alloy is notable for its high strength and is commonly used in aerospace structures. The 2290 alloy offers excellent weldability and retains strength at elevated temperatures, making it suitable for cryogenic application. This picture is the application proportions of various deformed all alloys in civil aircraft and the application of all alloys in Boeing 777 COMAC C919F of China and Japanese H-1 rocket. From the 1916 onward, research developed high-strength alloy by reducing impurities and adjusting composition, leading to grades like 2124 and 2524, with the latter now often used in aircraft fuselages. Recent advancements include lithium-containing alloy like 2199 and 2060, which show improved toughness compared to traditional 2 triple X alloys. Despite their strengths, 2 triple X series alloys face challenges with corrosion resistance and weldability, prompting ongoing research into new corrosion-resistant alloys and welding techniques such as friction stir and laser welding. Overall, These alloys play a significant role in the aerospace industry, with continued developments aimed at enhancing their properties. This is table of mechanical properties of some typical 2XXX series alloys. The 7XXX series aluminum alloys are heat-treatable alloys primarily containing zinc, along with magnesium and copper, at 275 degrees Celsius. Zinc has a maximum solubility in aluminum in 31.6% Vg%, which decreased to 5.6 degrees Vg% at 125 degrees Celsius. While zinc alone has a limited impact on strength and is prone to stress corrosion cracking, the addition of magnesium and copper during aging significantly enhance strength by forming hardening phase such as MgZn2 and Ol2Mg3Zn3. These alloys are characterized by ultra-high strength, often exceeding 500 MPa, making them suitable for high-strength applications like aircraft structures. Common grades include 70, 75, 74, 75, 70, 50, and others. The 70-75 T6 alloy mark a significant milestone in aerospace application, though its use is limited by issues like low damage tolerance and corrosion resistance. To improve performance, researchers have optimized heat treatment process and alloy composition, focusing on reducing impurities like silicon and iron that lead the brittle intermetallic compounds. Innovation have led to the development of high-purity alloys such as 74-75 and 70-50, which exhibit better toughness and are used in various aircraft components. The 7XXX series continues to evolve with research focused on enhancing strength, toughness, and corrosion resistance, including the exploration of lithium-containing alloys. Overall, these alloys represent the highest strength aluminum materials available, crucial for demanding aerospace applications. This is a table of chemical composition of some typical 7XXX series alloys. And this is a table of tensile properties of several alloys, 2XXX and 7XXX series alloys. Alloy alloys are heat-treatable aluminum alloys that incorporate lithium to create some of the lightest aluminum-based material available. These alloys found in the 2XXX, 5XXX, and 8XXX series can reduce structural weight by 10 until 20% when Li is added, with a 1 Vg% addition decreasing density by 3% and increasing Young's modulus by 6%. The initial generation of alloy alloys developed by Alcoa in the 1950s faced limitation due to poor heat resistance and toughness. The second generation emerged in 1970s and 1980s, fueled by energy crisis, featuring alloys like 1420, 2090, and 1890, which found application in military and aerospace sectors. However, they still had issues with anisotropy and weldability due to high lead content. To address drawbacks, researchers optimized alloy composition, incorporating elements like titanium for grain refinement and magnesium to enhance precipitation behavior. The third generation of alloy alloys has improved properties with lower alloy content and enhanced corrosion resistance, weldability, and strength. Representative grades include 2195, 2196, and 2099, which are used in various aerospace applications such as the space shuttle and commercial aircraft like the Airbus A380 and Boeing 787. Recent advancements in manufacturing technologies, including superplastic forming or SPF and friction stir welding, have further propelled to the use of alloy alloys in complex aerospace components. Overall, alloy alloys present a promising solution for lightweight, high-strength application in the aerospace industry, showing better properties than traditional 2XXX and 7XXX series alloys. This is the table of chemical composition of some typical alloy alloys. And this is picture of typical application of all matrix composition, tank and drill pipe on tank U2 to lunar rover. Tensile properties of wall structure, all 3 TI particle reinforced AMCs, and tensile properties of NEB4C all and MEB4C all reinforced AMCs with different mass fraction. This is table of comparison of properties of all matrix composites and all alloys. Particle reinforced aluminum matrix composites are increasingly utilized in aerospace application due to their lightweight, low density, excellent wear resistance, and fatigue resistance. These composites are suitable for extreme environment, making them ideal for components like aircraft wings, engine parts, and lunar mission tools. For instance, the Chang'e 5 probes drill pipe and the U2 to lunar rovers will power reinforced with silicon carbide particles, providing excellent corrosion resistance and thermal stability on the moon surface. EMCs can withstand the lunar temperature extreme of minus 127 degrees Celsius to 183 degrees Celsius without deforming, thanks to their high rigidity and low thermal expansion. Additionally, incorporating nanoparticles like Fe34 304 can enhance the magnetic properties of these alloys, expanding their application in aerospace. Cast aluminum alloys are typically used for complex components requiring toughness, while the formed aluminum alloys are better for high-strength, simpler parts. Other reinforcement materials such as Al3Ti, Al23, B4C, TIC, and TIB2 also show significant performance improvements. For example, multi-scale Al3Ti particles have demonstrated remarkable increase in ultimate tensile strength and yield strength with minimal loss of elongation. Research has shown that different particle size affect the strengthening mechanism during deformation, with nano-sized particles better at inhibiting grain growth, while micro-sized particles are more effective at dislocation inhibition as strain increase. Overall, the addition of reinforcing particles leads to fine-grain strengthening and R1 strengthening, enhancing the mechanical properties of aluminum alloys. Okay, we go to topic 3. This is a main strengthening strategies of all alloys. The chemical composition of an alloy is crucial for its microstructure and performance. By altering elements' content, one can change the types, shapes, and quantities of base friction. For example, the strength of each hardenable aluminum alloys, like 2XXX and 7XXX series, is influenced by the size and distribution of aging precipitates.
which can be optimized by adjusting the alloying elements. Research has shown that increasing copper content in all Cu MgAg alloys enhance performance due to the improved nucleation of the Al2Cu space. Similarly, increasing magnesium content in 7XX series alloys raise strength and hardness but reduce toughness. The zinc or magnesium ratio also affects performance, with lower ratios improving strength and corrosion resistance. Microalloying elements such as transition metals and rare earth elements can further optimize alloy properties by promoting nucleation of precipitates, changing precipitate types, and refining grain structures. For instance, adding germanium to AlCu Mg alloys accelerates aging response and increase hardness, while elements like erbium and scandium enhance hardness and mechanical properties through dispersed formation. Ultimately, while adjusting alloy composition can significantly enhance properties, additional methods may also be necessary for further improvement. This is a picture of E-timed gaps and corresponding selected area diffraction patterns in Al4Cu MgAg alloy. And precipitation behavior of alloys with low solid content and high solid content. Heat treatment is vital for enhancing the performance of heat-treatable alloys, particularly aluminum alloys. It includes three main processes: homogenization, solution treatment, and aging. Homogenization process aims to improve alloy uniformity by dissolving brittle intergranular phase that form during solidification. Proper temperature and time are crucial. Too slow may not fully dissolve phase, while too high can cause overburning. A two-stage homogenization approach has been found effective, improving the solution of eutectic phase. Solution treatment involves heating alloys to dissolve soluble phase before rapid cooling, creating a supersaturated solid solution. The solution temperature must be carefully controlled to avoid local overburning. New methods like contact solution treatment and electropulsion treatment have shown promise for improving the solution efficiency. This is a picture of common heat treatment process. All aging stretchness alloys, polarizing microstructure under different homogenization process and DSC curves, microstructure under different solution treatments, and morphology of precipitate phase and PFG zone under different aging parameters. 3. Aging. Following solution treatment, aging enhances strength through the precipitation of fine particles, either at room temperature or at elevated temperatures. The aging process affects precipitate characteristics of and influence strength, hardness, fracture toughness, and stress corrosion resistance. Advanced aging methods like retrogression and rigging and non-isothermal aging have been developed to balance mechanical properties and corrosion resistance. Overall, optimizing heat treatment schedules can significantly enhance the mechanical properties and performance of all alloys, but challenge remains in applying these methods to larger components. This is a picture of tensile properties of TiB2 particles. Reinforce different systems of alloy compared with alloys in literature. Ceramic particles such as TiC and TiB2 serve as stiff effective reinforcement in aluminum matrix composites and can also enhance the microstructure of metal alloys by refining grain size and improving overall properties. Research indicates that even small amount of these particles can significantly strengthen alloy by altering microstructural features like grain size and precipitate characteristics. For instance, adding 0.7% TiB2 to an Al7Ci4Cu alloy results in substantial improvements in yield strength, ultimate tensile strength, and elongation. Similarly, TiCN and TiB2 particles in AlSiMg alloys promotes nucleation and inhibited grain growth, resulting in a favorable balance of strength and plasticity. Further studies show that incorporating TiB2 and TiC into AlZ and MgCu alloys reduce grain boundary secretion and improve the alloy's response to heat treatment and deformation, leading to increased strength along different extrusion directions. Nanoparticles also enhance properties after processes like friction stir welding by preserving fine grains. Overall, this practical reinforcement in aluminum alloys offers a promising avenue for improving mechanical properties by manipulating the multi-stage microstructure during solidification and deformation, indicating significant potential for future development. Topic 3 is characteristic of advanced all-alloy forming and processing methods and possibilities for aerospace application. Additive manufacturing or 3D printing is an innovative technology that uses metallic powders or wires created by computer models to create high-performance structures by melting materials layer by layer with tools like lasers and electron beams. This approach enhances design flexibility and allows the production of complex geometries with minimal processing. The most commonly metallic EM techniques are powder bed fusion, and direct energy deposition. PBF involves spreading metal powder and selectively melting it with a laser or electron beam, including methods like direct metal laser sintering and selective laser melting. DED methods such as laser engineered net shaping and wire arch additive manufacturing melt powder or wire as they are deposited, making WEEM suitable for producing large aluminum alloys. Despite its advantage, the EM of aluminum alloys face challenges due to their physical properties. For instance, aluminum's high reflectivity limits laser energy absorption, leading to issues like inadequate melting and porosity. Additionally, volatile elements in certain alloys can cause defects during the process, and the formation of columnar grains can result in anisotropic properties. This is a table of comparison of tensile properties of 2XXX, 7XXX, and all Li series alloys prepared by EM, G, and L represent transverse and longitudinal direction, respectively. And this is a picture of diagram of SP technology and tensile properties of some 2XXX, 7XXX, and all Li series alloys by SP. Currently, all Si alloys, particularly all Si10Mg and AlSi12, are most commonly used in EM due to their favorable fluidity. However, the ultimate tensile strength of these materials typically does not exceed 400 MPa, which restricts their use in high-performance applications. To address this, researchers are developing high-strength alloys such as scalum alloy developed by Airbus, which has a tensile strength of 502 MPa. Other advanced alloys like 7S are being used in aerospace application, achieving strengths over 600 MPa. Efforts to improve EM of aluminum alloys include alloying, adding grain refiners, and optimizing processing methods. Recent studies have shown that specific alloy composition can produce properties comparable to those of traditionally reformed aluminum alloys, enhancing their potential for high-end manufacturing in aerospace and other industries. This is table of tensile properties of some 2XXX, 7XXX, AL-LI series alloys by SP. This is pictures of schematic diagram of 4 large plastic deformation methods. Rapid solidification or subrapid technologies involves a significantly faster solidification process than conventional casting, leading to enhanced solubility, refined microstructures, reduced segregation, and the formation of metastable phase in alloys. Two key methods of HRS are two-roll casting and spray forming. In the RC, studies have shown that SRS results in smaller secondary dendrite arm spacing and improved solid partitioning. For instance, by alloying with chromium, research transformed a acicular or bracelet-shaped face into smaller, evenly distributed polyhedral face, leading to increased yield strength, ultimate tensile strength, and elongation compared to traditional casting. SP technology involves atomizing molten metal with inert gas and depositing it on a substrate, which helps reduce oxide content and solve issues like microsegregation and cracking. Alloys produced via SP, such as the 2195 ALI alloy, exhibit finer and more uniform microstructures, resulting in significantly improved mechanical properties. 350-100 higher UTS, 26% higher ES, and 54% higher EL compared to cast counterparts. Additionally, the use of SP over ALZ in MG and CU alloys results in ultra-high strength of ES 869 MBA and UTS 879 MBA, attributable microstructural refinement and the formation of dislocation during processing. Overall, SP technology offers substantial benefits for aerospace aluminum alloys, showcasing superior mechanical properties compared to traditional methods.
This is table of tensile properties of some 2XXX, 7XXX, and ALLI series alloys by SPD. This is table of chemical composition of several ALFE PESI and ALFE MUSI alloys. Mechanical processing technology plays a crucial role in enhancing alloy properties and microstructures. Plastic deformation is a novel treatment that refines grain size, saving ultrafine grains and significantly improving performance. KFPT methods include equal channel angular pressing, high pressure torsion, accumulated roll bonding, and friction stir processing. Equal channel angular processing or ECAP is made
is the method involves pressing samples through a mold to achieve large plastic deformation. Research shows that ECAP can break rod-like precipitates into smaller, evenly distributed particles, leading to increase in yield strength, ultimate tensile strength, and micro-hardness. High-pressure torsion on HPT. Torque is applied while pressure is exerted, resulting in high density dislocation that form ultrafine grains. This method has produced exceptional results, such as achieving of a yield strength of 1 GPa in 2025 all alloy. ERB introduced to address productivity limitation. ERB involves cutting and rolling metal sheets to accumulate strength, resulting in UFC materials. This method is suitable for creating multi-layer metal composites and has shown improved ES and elongation in alloys. FSP. This technique uses mechanical agitation and friction heat to dynamically recrystallize alloys, producing fine-grained structures. FSP can enhance ductility significantly without compromising strength, as demonstrated in various aluminum alloys. Overall, SPT technologies provide significant potential for improving the mechanical properties of aluminum alloys, particularly in aerospace application, with HPT emerging as a particularly effective method for strength enhancement. This is a table of comparison of mechanical properties of several high temperatures aluminum alloys. This is a diagram of comparison of tensile strength with temperature change of RS or PM, high temperature all alloy, and some traditional all alloy. Powder metallurgy is an advanced manufacturing technology that utilizes metal powders or mixtures of metal and non-metal powders to create metal materials, composites, and various products through forming and sintering. Its key steps include powder mixing, compaction, and sintering, offering advantages over traditional casting methods such as reduced manufacturing process, higher material utilization, and improved dimensional accuracy. PM can enhance alloy supersaturation, refine microstructures, and minimize segregation. Despite its benefits, aluminum alloys produced via PM often have issues primarily due to retained pores that lead to poor mechanical properties. To address this challenge, researchers have explored adding alloying elements and employing plastic for deformation methods like extrusion, forging, and rolling. For instance, the addition of magnesium has been shown to increase density and improve mechanical properties by aiding in the redissolution of aluminum oxide, enhancing sintering. Similarly, tin has positively influenced the properties of AlCuMg alloys. High-temperature aluminum alloys such as AlFeVSi and AlFeMoSi, prepared by rapid solidification and PM, exhibit superior ultimate tensile strength at elevated temperature compared to traditional alloys like 2024 and 2219. This is positioned PM technology as a promising option for various industrial applications. And last, future aerospace alloy requirements. The development of aerospace aluminum alloys is primarily focused on achieving lightweight designs while enhancing overall performance in areas like strength, plasticity, corrosion resistance, and fatigue resistance. Key direction for future development include 1. Optimizing alloy composition, tailoring the alloy composition and heat treatment methods to control precipitate types, quantities, and distribution for desired properties fits to various applications. 2. Particle reinforced composites. This is creating aluminum matrix composites reinforced with particles to improve performance and meet lightweight requirements. And last, advanced manufacturing technologies, advising the adoption of innovative manufacturing processes such as additive manufacturing, superplastic forming, and rapid certification to boost production efficiency and product quality. Overall, this advancement aim to meet complex demand of the aerospace industry. Okay, that's all for me. Thank you for your attention. I'm sorry if I have a wrong, then tell you about this. So thank you for watching.